All right. From here on in, for the rest of the course, we are going to assume that you know how to do a Lewis structure, that you know how to make it the best Lewis structure, and once you have that best Lewis structure, we now know how to, we need you to know how to do the electron geometry, determine its shape, because that shape is then going to tell us whether the molecule is polar or non-polar, and that's very important for the rest of the class, because that's going to tell us about the intermolecular forces and how it's attracted to other molecules, attracted and repelled. So now, though, let's start to use all that we've learned. And we're going to use it for something called molecular polarity. And the most important molecule that we have to know about for molecular polarity is H2O. It is a polar molecule made out of polar bonds. We will prove it. However, we will also need you to memorize it, and we will talk about it a lot. And most people, or many people at least, come into this course knowing that water is a polar molecule because that is such an important fact. Okay, so it's a polar molecule made out of polar bonds. Our process is going to be to draw the Lewis structure. Then look at the central oxygen. Note that it has 1, 2, 3, 4 electron groups around it. That means that the electron geometry around the central atom is going to be tetrahedral. Bond angles are going to be, well, the basis bond angle for tetrahedral is going to be 109.5. We can see we have 2 electron pairs here. Electron pairs push the atoms to less than the ideal bond angle, so it's going to be less than 109.5 degrees, and that oxygen has an sp3 hybridization. Okay, so that's all the things we know from before. We can draw, and we have drawn, the H2O molecule in its correct electron geometry, tetrahedral, and what we saw was that there are 2 electron pairs, and we will now draw it a little bit differently. I'm going to draw it O, and then H, H, and again this bond angle should be a little less than 109.5, and I'm not going to actually draw the electron pairs because they're sort of going to get in the way this time, but they could be coming out and going back on this bottom portion of the O should we have drawn them. Although again, this is not the typical way that I draw tetrahedral. Okay, so the next thing is we're going to draw dipoles. And you draw dipoles for polar bonds. And polar bonds are, of course, bonds in which there's a difference in electronegativity. The way that I'm going to draw each dipole is with a plus arrow. That plus arrow is going to be pointing towards the oxygen, and the plus is going to be closest to the hydrogen. And these should be identically sized arrows because they have the same 2 atoms in each of the bonds, and so they should have the same size dipole. And then the question is, okay, so there's dipoles. How do we account and create what's called the molecular dipole? And to construct the molecular dipole, we first have to realize that a dipole is a vector, and a vector has both magnitude or number and direction. So a dipole is a vector with magnitude and direction. And so the magnitude, we said, or the size of the dipole, is generally going to go as the, or be proportional to the difference in electronegativity. So I'm going to write delta En here. And the direction, well, the direction is in the direction of the arrow. Okay? And we've simplified the case by having two dipoles that are exactly the same here. So we know that the magnitude is the same for these two. Now, to get the molecular dipole, you do vector addition. Of dipoles. And to do vector addition, and we are going to go through this from a physics point of view so that those of you who have had physics can relate to it, although we'll find many things that we need for everybody in this class. Vector addition of dipoles. Vector addition is when you place the dipoles head to tail. So I'm going to write vector addition of dipoles head to tail. And what that's going to look like is I'm first going to draw one of the dipoles with its magnitude and direction as best as I can. So I'm going to redo this dipole on the left here. Like that. And then I can never remember which is the head and which is the tail. Let's call this the head and the tail. Whatever I'm going to do, I'm going to put the plus part, the other side there, again in the same direction, or the same direction it's found. So these two dipoles are these two dipoles here. And then, so vector addition of dipoles head to tail. So the answer is by going from the beginning of one to the end of the last one. So molecular dipole, vector addition of dipoles head to tail, and then this black dipole is the molecular dipole. Start at the beginning of the first one and at the end of the last one after you've added them. So this is the molecular dipole. And that's how you do vector addition and apply it to doing dipoles. And we can see that the molecular dipole, when we draw it on the actual molecule, goes straight toward the oxygen from between the two hydrogens. And that's actually something, there we go. That's actually something that has relevance to us, because if you've ever used a microwave oven before, all it does is it takes the water molecules, oxygen, hydrogen, hydrogen, and it flips them, and it flips them as along the molecular dipole. So it flips them along the center line between the two hydrogens. Let me draw this. So this way, so it flips them like this along the dipole. And so and that's how a microwave heats food up, is it flips the water molecules by applying the right wavelength and frequency of to the water molecules to flip them. Now, what else can we learn from this without doing vector addition? Well, if I was just looking at this and I were to think of the dipoles as being broken into parts that go up and down, so this part goes down, and this part also goes to the left. This one goes down, sort of breaking it into what we might call the X and Y components. So it looks like the X components, one of them going directly to the right, the other one going directly to the left, would cancel each other out. And that's actually true. That's exactly true. And then the parts that go down, there's nothing to cancel them out, so they add. And so without doing vector addition, just by looking at the two dipoles, we can get a sense that it would go down. And the most important thing for us, we will see, is just knowing whether the dipoles cancel out or don't cancel out. And these definitely do not cancel out. That means, and I guess as our final statement, any molecule with a molecular dipole is polar. Any molecule with a molecular dipole is polar. Okay, and we'll do many, many examples of this, and this is our first one. And so H2O is a polar molecule made out of polar bonds. It is a polar molecule because it has a molecular dipole. And I guess the one other thing is sometimes because we're adding up the dipoles, we will sometimes call this a net molecular dipole, where net just means we've canceled out the left and the right parts here, and we have some leftover or net dipole. We've canceled out all the parts that can cancel out. Now, let's talk about CF4. It is a nonpolar molecule made out of polar bonds. We'll follow the same process. Draw the Lewis structure, draw the molecular geometry, and I can tell you, so the Lewis structure is going to have this basic idea. Lewis structures always have all pairs of electrons, so let's draw them all in. So many electron pairs. They're all on outside atoms though. Okay, so this is the Lewis structure for CF4. It has around the central carbon 4 electron groups. This is tetrahedral electron geometry. And we can draw this. I'll draw it down here. The only way that we draw tetrahedral in this course, like that. And remember, shapes do not have to have all pairs of electrons. And then from there we draw dipoles. Each of these bonds, because fluorine and carbon have different electronegativities, will have a dipole. And doing vector addition of these is not straightforward at all, because there's out of the plane, so this is not a flat molecule. However, we can see that the central atom is surrounded by all things that are exactly the same, and we have a rule of thumb. That is, when the central atom is surrounded by all dipoles that are exactly the same, and I'm going to amend that statement just in a second, actually. When the central atom is surrounded by only dipoles that are exactly the same, those dipoles will exactly cancel. To make a nonpolar molecule. Okay, so even though we won't and don't want to do the vector addition here, all of these dipoles do exactly cancel. This is a nonpolar molecule. Let me see, I can't remember if I have to do this example on this page or the next one. Good, we can do it on the next one. So now we have two molecules. We have, actually this works very well too. If we go back to water, or H2O, we see that there are two dipoles, but there are also two pairs of electrons. That is something different. That means that the dipoles won't exactly cancel. There will be a dipole, a net molecular dipole. This carbon has only dipoles that are exactly the same, no electron pairs. The dipoles will exactly cancel. All right, so again, we will do lots of examples of this. My next examples are going to be here. We're going to actually do this BF3. So BF3 is going to be an exception. If you remember, boron only wants 3 bonds. But this comes up enough that I want to show it. So BF3, start with your Lewis structure. And again, you would follow the process for doing Lewis structures, which would count up all the valence electrons, place the atom in the center that is least electronegative, etc., etc. Now, but this is the correct Lewis structure that we would come to. We can draw it in its shape, and I'm going to draw it as close as possible to the 120-degree angles. And then we can draw dipoles. The dipoles always face away from fluorine because it is the most electronegative atom. And we can see that this boron central atom is surrounded by all things that are exactly the same. We can cancel these dipoles out if we then draw, well, let's see, so we draw one dipole going up, that's the first one, and then we draw this one going down and then the other one going back. We actually get back to the beginning. So 3 dipoles that go back to the beginning means that these dipoles exactly cancel. No net molecular dipole. Colon, nonpolar molecule. Which I know it says right here, it is a nonpolar molecule made out of polar bonds. Our next example, ammonia. So draw its Lewis structure. From its Lewis structure, we can draw its shape. It's going to be tetrahedral. And this time, I guess I'm going to draw my pair of electrons on top. My 3 hydrogens going angled down and out. It will turn out that when we draw the dipoles, all 3 of those dipoles are going down at angles, and so the net molecular dipole, which I'll draw in red, goes, I apologize. I drew my dipoles incorrectly. I drew them in the wrong direction. Let me do that again. So I'm drawing tetrahedral with all 3 of these hydrogens angled down. That is a necessary part of drawing tetrahedral. And then my dipoles, though, face towards nitrogen because nitrogen is the more electronegative. And now my net molecular dipole, all 3 of these come towards the nitrogen. The sort of left and right or XY plane parts cancel out, and you're left with a dipole that's straight up. So dipole, the dipole points straight up. And again, so remember, a pair of electrons is something different. These 3 dipoles are all, so their left and right portions cancel out, but their up portion adds, and you get an up dipole. And the difference between the cases is, so this has 3 things and a pair of electrons, that's different. This has 3 things that are fluorines, no pair of electrons. And so this will be a polar molecule. Next one we want to do is C2H6. And we'll draw its Lewis structure. And we'll come up with a new rule of thumb for this one. Now I'm going to go ahead and draw this in what's called a double tetrahedral. And I will not ask you to do this. Let's see. Make sure I do it right. So, this is a double tetrahedral. It's got two H's coming out of the page at you. It's got two H's going back behind the page. And then this H, C, C, H are flat in the plane. And if we were to draw dipoles on this, let's see, carbon is more electronegative. And what is hard to see, very hard to see from this picture, is that all three of these dipoles and all three of these dipoles cancel out. So they're all pointed in opposite directions to each other, which, by the way, this is a single bond, so the bond is rotating. So all three of these are rotating and canceling out. This is a nonpolar molecule. And our rule of thumb is that any molecule made only of carbons and hydrogens is nonpolar. Any molecule made only of carbons and hydrogens is nonpolar.